right, sorry for the delay in starting here. So in the last lecture, we introduced this Excel-based numerical integration of dynamical systems. So basically we're implementing the example we did in the last one that had you add to it a little bit by adding this depth outflow. And I wanted people to kind of struggle a little bit on that and just to kind of get it fresh in the mind. And then today, in the lecture, I'm going to actually sort of tell you how to do the rest of the assignment. So, so it'll still be the same assignment due on Sunday, but you're basically just going to paraphrase or put in your own words what we'll do here. And, but it's not all for free. Then I'll give you a separate assignment, which is a slightly different system that you'll implement on your own in Excel. And then both of those are kind of part one and part two of this assignment. So you've seen the original problem, kind of struggled with it, hopefully kind of started to think about it, and then we'll solve on how to solve the whole thing. So you'll basically have a recipe for how to do the first assignment in this lecture, and then I'll give you a different assignment where you'll be simulating a slightly different system, but of similar complexity to this bacterial system, so you can practice what you learned. So that's the kind of roadmap for today. All right, there we go. So from last time, we're working with this bacterial example. We started with the banking example. We tried to turn the bacteria into a bank. So we know that we know how to calculate compound interest. Each year you have $1. After a year, you have $1 plus a fraction. And then we know that we can take that $1 plus a fraction from 1 year and we can put it in the balance of the next year. And then each one of those generates a little bit of a fraction. And then we take this whole new amount and it becomes the balance for the next year, and so on and so forth. And so we feel like we could generate an Excel spreadsheet that would simulate our bank balance over time. So our thought is, how do we take something that is a little more complicated than compound interest of the bank, so now we're talking about growth of bacteria, and turn it into a format where we're using sort of the exact same setup to simulate this growth. So the thought was here we have this more complicated system. Most systems in real life are going to be specified kind of like this. You've got some initial state, one bacteria, and you've got something that changes that state. Now when you go out and try to look for information on Google about how quickly things change, very often you'll just find these averages. We know that on average, if you wait W time units, let's say 0.75 seconds, you're going to get 2 bacteria from 1 bacteria, on average. So some bacteria are going to double in less time, some bacteria are going to double in more time. So the thought is here that I have some time instant where 1 bacteria goes to 2. Now, there could be some time period less than that, where the next duplication events. There could be some time period less than that again, where the next time period, the next duplication events, or we could get a little wider than that when the next duplication events. And so this can go on, but all we know here is that on average, if we wait W time units, like 0.75 seconds, then our population is going to double. Or every bacteria in the population is going to have an opportunity to duplicate. Now those that duplicate are going to then start duplicating themselves, and that's why it's not quite so simple as to say the whole population doubles. The population might get much bigger than that out of this 0.75, but on average, if you look at every individual bacteria, you wait 0.75 seconds and you get 2 bacteria from 1. And so we are going to use this averaging approach. So, and again, this is a bacterial example, but you can use this for thinking about the growth of a population in Phoenix. If you know, on average, those, you might say there's, out of every 10 people, only 5 of them choose to have kids. And of those 5, it takes them a certain amount of time before they're ready to have their first kid. So if you think about how many kids the group of 10 puts into the population and how long it takes for them to put into that population, you can come up with a similar story here. On average, every group of 10 people puts this many new offspring into the population after you wait an average of this amount of time. And that kind of smooth idea where we're going to take something that in reality is very discrete and it seems very random, and we're going to smooth it out and make it deterministic just by playing with the averages. That's the type of simulation modeling we're doing here. So we do that in the bacterial case by taking this realistic scenario, and we've already added the averaging, which adds a little bit of unrealistic stuff, but it makes it closer to the model. And then we turn it into the banking account example, where we say that just like every dollar we view as kind of bleeding out partial dollars, then we say every bacteria is bleeding out partial bacteria, and it's bleeding out at a rate of 1 divided by the doubling rate. And so this gives us a rate unit that if we multiply by the number of bacteria, we find out how much of a flow we get into this new accumulation of bacteria. And if we only look at how much adds in a very small amount of time that we're going to call dt, then basically we can calculate how many new non-reproducing bacteria are generated. And then when we move to the next time unit, we just take this new proportion, we add it to the reproducing proportion, and then we do that over and over again. We need to do this with a very, very small time unit, because while the bacteria are accumulating here in our model, in our spreadsheet, these new bacteria aren't reproducing. But in reality, they're in the population of bacteria, then eventually these bacteria reproduce. And so we don't want sort of a huge population of new bacteria that could be reproducing that aren't reproducing. That's why we only simulate this when we get a little bit of bacteria, then we go to the next time step and then redo our interest calculations. So that's kind of the banking model that we've got for why we're generating it this way. And so this is that, just graphically what I just said there. We have a stock of bacteria, our bank balance. For everything on our bank balance, we need something like an interest rate to figure out how much our balance will increase to the next year. So we generate this flow, and we calibrate this flow to be similar to that doubling time that some biologist or microbiologist has told us. The biologists tell us that we know that every bacteria takes on average W time to double, and so we're going to create a flow rate per bacteria of 1 over W. So if we take that flow rate, multiply it by the number of bacteria, and then multiply that by the dt, then that gives us our interest. That gives us how much we're adding to the next balance. And then we redo that again. So I just took this interest, I added it to the balance, a new balance, and now both of them are generating at this same 1 over W rate that generates new interest, and so on. So that's the basic structure of this simulator. And with it, we can then keep count. We had 1 bacteria in our balance, and then after we added the interest, we had this much bacteria, and then both of those started adding interest, and then we got that much bacteria, and so on and so forth, until we get this kind of exponential curve that we're expecting. Maybe you remember something like this from SOS 101, this exponential growth curve. And even though we didn't put in a formula for the exponential growth curve, using this year-by-year compounding interest by compounding interest relationship, we're able to get that same formula out. And so if we zoom in on one of these intervals, then what we see is we have the stock, the number of bacteria at the beginning of the interval, and the number of bacteria at the end of the interval. And if we were to create a slope in between those, if this dt period is really, really small, then what we're doing is we're approximating the derivative of the population growth by this slope. Because that's all derivatives are. When the time distance gets really, really small, then a derivative, which is like a speed, it's like how quickly is the population growing at this instant? Well, rather than formally modeling how quickly it's growing, then I'm going to just approximate what it's going to be at this next time instant. And I'm going to do that by making a guess at what the speed is and just projecting forward as if the speed doesn't change during this whole interval. And that's why I need to make these dt's small, because in reality, in the continuum of population, then this stock is constantly changing through this whole period here. But if I make the dt really, really small, it's like the derivative doesn't change much. So I can just guess that if the derivative doesn't change much, then it's just a constant slope, and that tells me what it's going to be over here. So this is where the calculus interfaces in what we're doing. When you are going to put in these flow expressions in the spreadsheet, We're not calling them derivatives formally, but that's what these flow expressions are, is that they are a way for us to put derivatives in, and we're actually modeling our bacterial growth by writing in formulas for the speed of the growth, and then letting the spreadsheet add all those speeds up together and see what sort of population we get out. So that's what we started to do last time. We said, okay, so we're going to build a spreadsheet that models the growth of bacteria with this 1 over W flow rate. Now what I asked you to do in part 2 was to try to use what you learned from part 1 to add an outflow, to add a death rate. And this is what I'm going to sort of show you how to do now, but what I'm hoping that you started to see is that the same logic here. This logic was that we get a birth event every W time units. And so we're going to simulate that by multiplying the current number of bacteria by 1 over W to figure out what the flow of new bacteria is at any instant of time. The death is identical to that. We don't go down to like the 3rd time unit in the simulation and then start changing the formula there. That's not what we want to do. We want the same formula on every row of that spreadsheet, from the first row all the way to the last row. And so we have to say, at the first row, what's going on? Well, every bacteria, we're saying on average, goes through a death event every 3 time units. And so what we're going to do is create an outflow column that looks just like the inflow column, but instead of multiplying the number of bacteria by 1 over W, we're going to multiply the number of bacteria by 1 over 3. Where W was 0.75 in your example, this is how long we wait until that bacteria doubles. And then 3 is how long we wait until that bacteria sort of vacuums up another bacteria. It gets rid of itself from the population. But in terms of flows, this is just 2 different types of flows, an inflow and an outflow, and we model them the same way. What's the average time until we expect the population to change? And that's what we'll see more concretely. So the net effect is that the flow is going to be not just the 1 over W flow that you had last time, but it'll be 1 over W minus 1 over 3 times the number of bacteria. So that's what's going to be when you're calculating the number of bacteria in the second row based on what's in the first row. It's going to be that first row plus this times the number of bacteria from that first row, and you're going to fill that all the way down. And if you adjust the death rate, you're just going to be adjusting the waiting time until death here. If you adjust the birth rate, you're going to be adjusting it here. But you only have to adjust it in one place. You don't have to manually go down and find that row of your spreadsheet and start inserting new formula there. So let's see how that works. So this is a cartoon example of what we're implementing in the bacteria, or in the spreadsheet. Is that we've got number of bacteria currently times 1 over W, number of bacteria currently times 1 over 3. That's the inflow, that's the outflow. In our spreadsheet, we're going to add that minus that, and then that whole thing gets multiplied by our little dt time step to find out how much action happened in the tiny little time window. And then we take that little amount of interest and we add it or subtract it, whatever it might end up being negative, to the balance, and that's how we get the trajectories all the way through. So that's our cartoon example, but I'm going to now show you sort of on the spreadsheet what that looks like. So here's what we had last time, but I've added an L up here, where L is my length of lifetime. So before we had a dt, and we had W, where W is like waiting time until you produce a new bacteria. So now I've got L, which is like the waiting time until the lifetime ends. And just because to get us into this rate mindset, it turns out that for system dynamics modeling, it's just much easier to talk in terms of rates. So if you look up online, you're going to find data in terms of waiting times, how long until an event happens. But it's easier to convert that into how often does the event happen. And so in this case, we just do 1 over the birth rate, and that tells me how many new bacteria do I get per second per bacteria. So that's what I mean by rate. It's just 1 over these things. Similarly, I'm going to create a death rate, which will be 1 over L. So it's just a rate. How often so I get this many births per second per bacteria, this many deaths per second per bacteria. And with those two things together, I can now take the spreadsheet that you were working on last time, and I can add my outflow. So here's basically the spreadsheet you had before, but I added the L. Here's the birth rate and death rate, which are just 1 divided by these two things. And then I have a time column, which I start at 0, and every column I add my DT. That's what that $B, $1 is. And then I move over. I start with 1 bacteria. You could start with 50, but we're just going to initialize at 1. That's our initial condition. Here, I need to figure out the number of births. Well, that's just the current number of bacteria times the birth rate, which I defined up here. I then need to figure out the number of deaths. Same idea. Current number of bacteria times the death rate, which I have here. And now I have everything I need. Well, I need one more thing. And then, how do I figure out the next number of bacteria? Well, it's just the previous number of bacteria plus dt times a sum of all the inflows minus the sum of all the outflows. And that's the formula I have here. Previous bacteria, dt, inflows minus outflows. And with all of that, if I fill down, then I will simulate a bacterial population with both birth and death. And up here, I can play with the birth rate and death rate and see how it changes the trajectories. I can get growth, I can get a constant population, and I can get a decline until 0. So that's what I would do here, and there's an example. So there are questions. I'll go back and here. There are questions about this formulation, about anything that I said here, about why do we do it this way, or any questions from last time. Does it make sense that I'm turning, if it makes sense how I built the births, then it should make sense how I built the deaths. But it's totally reasonable if how I got the births is still unclear. So do we have any questions about any of that, any of these formulas? Yeah.
Would you just get rid of flow of new bacteria? Like for the first part of the question, would you just put that comma, or does that become birth?
The flow, for the first question, that's like getting rid of the death column. The first question was just to reproduce what we did last time. And last time we didn't have deaths. And you could simulate getting rid of the deaths column by making this L gigantic. Like if you put this as like 9 million or something here, then basically the death rate would go to 0. And it'd be like zeroing out this column. Or you could just remove this column from the formula here, and then you would get the same thing you implemented last time on Tuesday.
Okay.
Does that make sense? Any other questions before we move on? Yeah?
Why is the second time 0.01?
Because if I go back to this column, how I do my time, every time step is dty. And so I start at time 0, so the next time step waits 0.01, and that's why it becomes 0.01. It becomes 0.01 here. As I fill down, so if I go to the spot after I fill down through these, then I see 0.01, 0.02, 0.03, each one of these are 0.01. So in the assignment, I asked you to simulate this up through 5 time units and call them 5 seconds. If you change your dt, then like if you make this really small, then if you don't change the number of rows, then your plot might end like at 1.5. And so in that case, you need to fill out the number of rows so that you get enough rows to go back out to 5 again. Yeah.
In the birth and deaths column in CMD, are those actually rates?
Are those actually rates?
They haven't been multiplied by the time rate.
That's right. So you can think of these as per bacteria rates, like per capita rates, and these are population level rates. So you're taking the per bacteria rates, multiplying by the number of bacteria, and getting the actual change in the population over time. Yeah, so I said births and deaths. This really probably should say birth rates, death rates. I think when I made these slides, I didn't want to be confused with this, and I also didn't want this to be super long and say like birth rate per bacteria. Are any other questions about this? Okay. So then the third question on that says, what happens when you change dt? So here is my original dt of 0.01. And notice that it starts at 0, and at time 5, it goes all the way up to 140 something, like 147 or something like that. If I make my dt much smaller, and I have to increase the number of rows, but I get basically the same curve out. Notice it's not quite as chunky. There's like steps that you can see here. And because I've made my dt, I've basically cut it, divided it by 100, so my dt is really small. Then you can't see these chunky steps anymore, so you get a nice smooth line, but it still starts at around 0, 1, and it goes to about 147. So that implies to me that 0.01 was probably a good dt to choose. But maybe I want to try a higher dt than that. So I might go to all the way to 1. So now I've got a dt of 1. And so now I get this plot. Now you can see, if you look closely, there are little corners here every 1 second. So if you see it's hard to see here, but there's kind of a little corner there. There's a much more evident corner here, much more evident corner here, and so on. And that's because these are the only spots where we're updating our population approximation. The blue line in between them, that's just Excel connecting the dots. And so in this case, I'm taking a gambit by choosing dt equal 1 that I can assume that basically nothing happens in 1 second. And so I can take the number of bacteria at 1 second, calculate how many bacteria will be generated in a second, add that, and jump all the way to 2 seconds. But if I generate a lot of bacteria in 1 second, then they would have reproduced themselves during that interval. And I'm missing out on that. And that's because, and that ends up being the reason why, if I look here, after 5 seconds, I am at a much lower population count than I am for the other DTs. So basically, by taking the chance that by trying to simulate quicker. So here, there's basically only 5 rows, 1, 2, 3, 4, 5, and then 6. So this is our initial conditions and then 5 calculated rows. I tried to get away with only using 5 rows of an Excel spreadsheet, but it turns out that that's probably just too coarse because I'm jumping over so many things, I'm just assuming they're not actually happening, that my bacterial growth ends up not being where it should be. And that's, now if I would have changed my birth rate or my death rate to be much, much faster, then eventually I would get the same problem with this one. So that's the idea, is you have to choose your DTs values to be basically much smaller than the time scale of your system. And the fastest thing that happens in our system is the birth rate at 0.75 time units. So because the birth rate takes less than a second, then it's really important for me to not try to simulate over the birth rate because I'm going to miss a bunch of births. And that's the reason why these two look the same, but this one looks different. So we want to make our DT as large as possible, but we want to make it small enough that you end up not getting this giant change from here to there. So any questions about that, this idea of making the DT too big? And that's the third question on that, is can you generate at least 3 of these graphs that demonstrate this, and then say in words to me what's going on. So then paraphrase me in your own words how to choose a good DT and what the problem might be by choosing too large of a DT. Yeah.
So then you want DT to be smaller than the difference between what the person does? Is that what you're saying?
Well, I don't exactly know how much smaller. That's hard to say because especially when these systems get really complicated, but effectively that's it, is that I want the DT to be sufficiently small that if I made it any smaller, I wouldn't get any change in the curve. But as large as possible. So if I make it this large, it's bad, because if I make it a little smaller, I get a very different plot. But there's no reason for these settings for me to make it this much smaller, because this curve is basically identical to this curve. All right, any other questions about that? All right, good. Well, so that, so this is just exactly what I said here, finding the right DT. Too large and your simulation's inaccurate, too small and your simulation takes too long. So that's the balance of those two things. So any other questions? That was all of that first assignment we did on Tuesday. Yeah.
I have the exact same like data as you, but my graph is not like exponential, it's just a straight line.
Oh, okay. Well, it might be. So if you just have a straight, you say the same data.
That's the one. Axes are completely different.
Right. So there's a question here. It said I just generated. I used the same formula as you did, but when I filled down, I got a straight line and not an exponential. And the reason that's happening in your case is that if you look at your time, you're only filling down to like 0.004. And so you're simulating this tiny little bit here. It's zooming in on that. And so it looks flat. If you continue to fill down so that until this time column says 5, you should get that. Does that make sense?
Yeah.
Okay.
When you said 5, I thought you meant 0.05.
Yeah, so that's a good question. When I say 5 in the assignment, I don't mean 5 steps. I mean 5 time units. By time units, I mean I didn't give you a time unit, but I mean like seconds or hours or minutes. So whatever time unit is being expressed here, I want you to go to 5, not 5 steps. So all the way down to the number 5. So this might go down 5,000 lines until you get to number 5. But I want you to have this go all the way until that reads 5. All right, any other questions? All right. So this is basically a summary of what we've been doing. We're going to be, next week, we actually go into drawing these in this form, where this form, this is the stock column, this is the flow column, these are any auxiliary columns you put to help you do the calculations. But what you're doing when you write these stock and flow models is the equivalent of this integration problem up here. So the formulas you put into flow, if you were to then take them and integrate like you do in 211 and get something out and then plot this thing, it should match the thing that comes out of the Excel spreadsheet. So this is our shortcut to getting that without ever having to actually go through the calculus. That's what these numerical simulations are doing. And so this here is how I would draw this in those stock and flow diagrams we're going to learn more about next week. So I've got a bacteria stock, I've got an inflow of births, there's a birth rate and an average time to reproduction, there's a death rate and an average lifetime. This is the stock and flow version of the spreadsheet that you just saw implemented over here. And that is the calculus based in a differential equation, but all 3 of these things are identical. But we're trying to get to the solution of this without having to do the integration. And this is still tedious. So you start here, you gotta walk before you can run. But when we run, then we get to draw them out, and this is much, much easier than dealing with any of this stuff. And yet, this will give us the exact same curves that we would get if we solved this thing by hand. So that's where we're going. All right, so any questions about that before we go to the next assignment here? So the new assignment, now that I've done the first assignment for you, is a simpler, it's equally simple, but it's a very different context. So you're basically building a spreadsheet modeling how water fills in the back of a toilet. So you assume that you just flush the toilet and the water level is 0 centimeters above the bottom of the toilet. There's a target water level of 15 centimeters, and you have got a flow which is regulated by the valve in the toilet, which gradually gets slower as you get closer to the target. So initially, it's a full, whatever this, it's proportional to the height of and so it's initially 15 centimeters, but as you get closer to the target, then it goes closer and closer to 0 and eventually shuts off. So you're going to simulate this using an Excel spreadsheet. You're going to plot the water level as it changes over time, and that's going to require you to choose a sufficiently small dt to be a good approximation. Make sure you label things with titles and units like seconds and centimeters, and then again show at least 5 seconds worth of data from this simulation. Submit it within a Word document, also submit your spreadsheet, and then show me a causal loop diagram showing this. And as a hint, it should be a balancing feedback loop. It should be a relatively simple loop, similar to the other balancing feedback loops we showed, plus single loop. And then I've added extra credit, if you'd like to do it, where you can complete this first part again, but add a leak. And that's equivalent to like adding a death rate. And so if the toilet is leaking, then how does that change the level at which it settles out at? And so describe whether you think it's approaching the same level as it was without the leak. So that's just for extra credit here. So that's basically, this is basically implementing this example, but with a toilet instead of a bucket of water. And so there's our toilet. We've got a target level coming in. That's setting up the flow. We've got a water level here. So this is going to be in the flow column of your spreadsheet. This is going to be in the stock column of your spreadsheet. You can put this as a parameter up top, just like the kind of birth rate. And that's it right there. That's it kind of symbolically. And that's the formula you'll put in that flow column. That's maybe what's going to be in the stock. And so you'll implement it in this way. So you'll have the water level is going to be a stock column. The valve flow is going to be a flow column. If you need any extra columns, you can add them in as converters, and then you'll simulate that down. So that's this assignment, which is, I'll help you with, because we're going to start that now. Are there any questions about this toilet bowl example, implementing it in Excel? The formulas, I think, are going to be a little simpler than the bacterial ones, because there's less multiplication going on to worry about. Okay. So looking forward, think about starting reading this chapter 3. That'll be due basically in a week. Again, I mentioned it last time, start forming your final project teams. It would be a good idea to get an Insight Maker account. Unless you really like Vincent, you can use Vincent as well for all the Insight Maker stuff. And we'll go over how to use both. And then assignments for this week, there's these assignments D1 and D2 are kind of like part 1 and part 2. All of the solutions for D1 are in this lecture, so I'm just asking you to parrot them back to me in your own words. And then D2 is your opportunity to practice what you learned from D1 to implement this simulation of a toilet, and we'll use the balance of the class, and I'm happy to help you get started with that. And so that's what we're going to do now. Midterms coming up after lecture D4, so basically after Thursday of next week, we'll get a weekend, and then that Tuesday we'll have a review lecture in class, and then that Thursday you'll have the first bite at the midterm. And you'll go over the weekend, and you should get your scores back by the end of the weekend if the library goes quick enough. And then that upcoming Tuesday, there's a retake. And it'll be a slightly different midterm, but same number of questions, same difficulty. And then the Thursday of that week, which is right before finals week, we start lecture E1. So if those of you are okay with taking that as one of your misses, you can feel free. We've got no assignments like that are due in class that day. And then you'll go off to spring break, and you'll come back, and we'll keep going with Unit E. So that's where we're going with that. So any questions? If not, then we'll do the attendance exercise, and we'll do the toilet assignment, which we can work on until the remainder of class. Question?
What's the date of the meeting?
It's if you go on to I don't want to say the wrong date. If you go onto Canvas and look under the course. Information module, there's like a tentative schedule. If you click on that PDF, it has a date of all the lectures and the midterm retake. Any other questions? All right, the attendance exercise today is the attendance exercise for Tuesday. I asked you what the derivative was. Was it a stock, flow, or converter? And the right answer to that one was that it was a flow. So my question was, in the bacterial example, what role do the bacteria play? Are they the stock, the flow, or the converter? Yeah. Oh, you want one? Sorry. And so the question is, in the bacteria example, are the bacteria the stock, the flow, or the converters? Yeah, I'm sorry.
Just thank you for reaching out to me and comments today.
Oh, right, yeah, sure.
I think,
Well, I mean, thanks for submitting something early.
yeah, so I think you're it out more so.
Yeah, it looks like, I mean, I have to look at the formulas to be sure, but I mean, these are kind of the right,
The numbers.
yeah, I mean, they look like they're heading in the right direction. And you can double, oh, right, I haven't put the depth, oh, yeah, I have, so
Yeah.
you can double check, and if your, like, first 10 columns, or 10 rows match my 10 rows, that's a good sign.
And then for the other three, am I okay to not have the depth on there, or do you want the depth
Part, part 3 was,
for the GD or DT?
as long as you make a good argument, you can make an argument with it without it.
Okay, cool. So when you said it was unfinished, because I didn't have the argument in writing.
Right, you just sort of gave me 3 plots, and so I was looking for you to like explain to me how.
I wasn't sure because it was
Yeah.
kind of pickled.
So if the attendance is done, I'll flip back.
Confirm my group size?
We want groups of 4.
Perfect. Thank you for that. Alright, so we're first. I don't know what I want to start.
And then right here.
You just do it. I know. Oh, wait, what's talking about? Oh, the homework. Oh, yeah, just do it.
Sometimes you enter the slide, sometimes it's used that you just I think it's in general, but because maybe you entered it with the slide, 0.3 or 1/3. Yeah, so it probably took it as yeah. So it's just like it's trying to make it easier for you if you are using it.
Can I have my brush?
Not if you enter your
Is that what it's supposed to look like? Oh, that's what, you know what's funny is remember in class when we did that too, and said, oh yeah, you should do it, and now I'm doing that. Yeah, isn't that so?
It looks like the rate of question generation slowed. We're gonna take off.
Why did I just do this? I just
That's what I thought. Oh,
can't see a lot. You're only laughing at her because you got annoyance in your voice. Yeah, but there was no shit. But it's yeah, but I just like I shut down.
I like tests
in one day.
That's just sort of like those days like
How do I delete this? Right? 1, 2, 3, 4, 5. Why? How do I just sit there and oh, because it's 0.
So yeah, that's the tricky thing. So what we're saying is that there's a, rather than thinking of it as like, there's an instant where death starts, what we're thinking is sort of like every bacteria is sort of continually dying. And so that's the kind of smooth approximation. So we have one bacteria, and in the DT it's going to lose a third of itself. No, there's only one, well, I mean, there might be a way to interpret it that way, but I would say that this approximation assumes that every bacteria is pushing out new bacteria within 1.3 and is gradually itself being reduced by 0.3. Does that make sense?
That's the goal that you see.
Okay.
So when it reaches 15, the water goes.
But L is water, that is correct. Well, you already have it actually. So it's called L here, but we call it water. Right now, it's like, effectively, you couldn't mention L. It's like L, you could just put it in the name of water. It's already LND. Oh, well, there's no wait, so that's the thing, so the waiting time, that one is just for the bacteria. So this is going to be a little simpler than that. There's no discrete events in this toilet cleaning. You don't have to have like a waiting time. All we have is like flow, so you basically don't have to stop the water. And that flow column is that thing on top that's the flow. So it's how quickly is the water changing. And so column C would be your like flow. And basically in column C, it's just going to be that formula where it's going to be whatever your set point is, which you can write around at the top if you want to. Minus the current state.
Oh no, this is the bacteria.
Well, so there's you've already how much to put in at first is the water level, which you've already put in at 0. You're saying it's where that's right. So you got that right. That's correct. So the flow is basically just that formula. So you would put like equals 15 minus. And that's the flow. So you're getting into here, but that's basically telling you that when the valve opens up, it's going to create a drop of it's going to do a flow rate of 15 centimeters per second. And so your DT is going to, so you need to specify a DT, which it's probably easier to specify like above, kind of like we did here. So like let's insert a couple of rows. And the DT is not going to show the two, it's going to be like this separate parameters.
well, like end up having to do so should we, when we input the DT, should we make it so that this is like
Well, then, like, this is one of
B equals
that one over the time.
There, I think.
I mean, it doesn't, I don't think it.
Like for your cell 4 or whatever A4 there, it should just be whatever the previous value is plus DT. And then we use that formula for the whole thing down. So, so like, yeah. It's, so, that's right. And then
is that too low though? Because this feels like a lot.
remember, you only have to go up to 5. So you've got, that's 15. Yeah. You can go 15, you just have to go down to 5. So I think what you probably need to do is you still have the very top.
Yeah, so they need to
Either 8 or bigger. I would just say either equals A3 plus DT.
well, it might be something similar.
And then so you do plus, and then the cell right above it, which is A3. So that would be the easiest. So it's only A4, and that A4 would just be equals A3 plus dollar $. So that's the thing that you can graph. So not it's just that way. So this like a second DT to like 101. And then for your first time, you set that so that so the second time is going to be equal to the first time plus the DT.
The ones that needed to be. That are starting, yes. It's that.
So if you're there, if you say 101, if you fill that down, you just mark it.
Yeah, it says charity, that we don't have to.
The stocks always have this formula where it's like previous stock plus flow times DT. So what's the previous value of the stock? Good.
You can do it. No, that should work. Maybe it's because you have a.
So now, you have
You're telling me.
Because it does it according to the length of the column next to it. And because that's blank, it doesn't know where it stops.
Yeah, well, effectively what you're doing is actually not intakes. You put in a total inventory, and over time, you use these rows as full. So that initial 0 is like you're saying, I'm putting in inventory, and now I'm going to apply zeros.
See, there's no formula.
And a good place to start would be, one of the slides here, I say like generically, these are the stock columns, these are flow columns, these are you start with that, and then you just kind of look up and say, all right, what are my stocks right now? And then you replace stock 1 with L. What are my flows now? Replace flow 1 with flow, and then the formulas as they connect them. And then you end up with something like this, the columns you don't need, remove not, if you simulate that thing now until DT is equal to 5, then you should see a water level that has a shape that looks like that, and a flow that you run in. Yeah, well, I would call the C10 minus D10 a net flow, and C10 would be an inflow. Yeah, that's kind of what I would draw up there. Flow is for T minus L, where L is the stop.
Okay, so for my second one, maybe not 0.01, it says to restate from 1 to D1, and then D1 example that the outflow column or D3 was 0.1. So do you want me to change this to 0.01 so it follows the rest?
No, I think it's, I don't think this, I'm pretty sure on the rubric we don't, we're not looking for it. So as long as the shape is right.
Because then like for my second one, I did 0.01, so go a better curve, right?
Sure.
Okay. That was
Oh god. Oh my god, wait, did it just go to everyone? Oh god.
Yeah. Oh, right. Whatever you would like. I would, we're not gonna like take off, as long as the shapes look right. No, I would say don't make it in one, but make it sufficiently small that you get the right curve.
Yes, I remember that. It was the same so exactly.
Oh, wait, did you? Yeah.
It was first decided.
Oh, I saw it, it's literally, yeah.
Okay.
Doesn't even make sense.
I don't know what it was.
Yes, so, it just, it's pretty minor, but, so, I think the big issue here is you've got the dollar signs and the net flow. And so, you want to, the dollar signs you want to be on the DT, but not in those, so you get rid of the dollar signs in this net flow, because you want the net flow to actually, to always refer to the immediately previous row. But by putting the dollar signs in, when you fill down, it keeps them. So if I were going here, they're staying up. Even though in row 14, so when I'm in row 14, I will go to row 13. So in row 10, it will go Pardon? Oh, that's yeah, get rid of the dollars, but keep them with the DTs. And that's just for your that level thing. And then similarly, if you've got, so like, I see your bird, so that's, so that would be the B times B5. That looks good, and then under that, that looks pretty good. So then, I think all that looks pretty good, so try and fill in that formula to be fixed. Yeah, not there, the next one.
I was trying to do this first.
Row 10. Yeah, try and fill in that. And it looks like now they're growing, and the birds are growing, bats are growing, so I think that's, you're probably good. So you have to plot it to be sure, and you have to fill everything.
Okay, thank you.
Yeah.
Oh, okay.
What's the problem?
Because you always want it to be referring to the previous stop, not the immediately previous stock, but then the DT, you always want to see the very, very top.
It's in the top of the set.
Oh, yeah.
That's where you should bring it down.
So, like I said, for this first one, we're talking about divided graphs, and here I just want to say problem one. Problem two, again, you can just show me. Problem three, this is actually what I want you to answer the question, how do you change the graphs? And you provide the graphs. I don't have to say that much, but you just say, you can change it this way. That just makes it great. You always have to update yourself. But also, if you see something weird, it's like, help for us.
Okay, so
So the stock would just be like how much is missing from here, so it would be like 15 minus.
No, it's you got it's actually flipped for that. So the stock is the flow is kind of like how much is missing, and the stock is how much is present. So the stock is always going to be the previous value of the stock plus the flow from the previous row times the.
So this should be the stock, or
No, you actually, the flow is included. The flow is just going to be 15 minus, well, actually scroll to the top. So there's row 4, so that's, as long as like that's 15 minus 4, that's 15 minus 5, and so on. That is the correct flow, but you also want to flow.
Not at all.
I would just be 15.
Well, it'd be 15, you still would be 15 minus 8. Yeah, it's basically the same. If you did it right, the same formula should work.
Yeah, that's what I said over there.
You don't have to do that. And then you're, so all you need to do then is go to stop. The second, that one there. That's just previous stop. It's like just like your time row. It's the previous stop plus
something a bit off
the
about.
previous flow times the t, where the t measures dollars. So
It did? Okay. I was like, it sounds like 14. But everything just
well, in this case, it says like the time call, so that would be the previous stop. So you're just constantly building on that. Oh, plus, because you have to have the accumulator. This is where you do the previous flow.
So B.
So you look under that flow column, and then that times whatever the DT value is, which is like E1, and that's going to take that's going to take the dollar signs, $V.
So B1.
Yeah, $V. Get into there. Then you see that you get a little bit of time. So as now you're seeing here that the flow is actually I don't know if your flow column is a little crazy. Okay, these should be 8. So I would go up to this first column here.
And then you can fill that flow back.
This one.
Do we just put
That's good. That's actually what you want. Because it's referencing the stocks column, you haven't filled the stock down. Oh, right. So now you can fill the stock down. So you're seeing that the stock is rising to 15, the flow is falling to 0. Exactly what you want.
Oh, nice. Then again, it makes sense now, just we have like a graph to illustrate this.
That's right. So you plot at least the water level. If you like, you plot the water level and the flow. I'll also recommend getting rid of the columns you don't need. Labeling these things like water level, water flow, stuff like that.
So, I have to stop.
No, it doesn't stop too. You can rename flow one and stop. What you get, you can right click on columns and say date. And it will automatically update the coordinates. Yeah, like the water level in the toilet starts at 0 and it rises slowly and eventually settles out at 15. That's right. Now, and then so, but then that's the bonus question. Is you added a little bit of outflow, how would it change that graph? And if you've ever lived in a house with an old toilet, you know that you always hear the toilet, but it still works. So you would actually see something similar. So it wouldn't like go down, but it would do something else. So that looks good. I mean, I would like actually like maximum use on all that sort of stuff, but it should just matter.
You know how to do that on Excel and have add titles?
Yeah. So if you see add chart element over there, and then you've got all the stuff there.
Okay, thank you.
Yep.
That's what my mom always yelled for across the house, so that we could go like this and go.
That's right. With dollars or oh, well, no, so you don't want the whole thing, just look like a flow. So it's the stock plus the flow.
Wait, no, April.
That is, there's no DC involved. And if you fill both of those in, you should get a rising water level.
This year.
So like, is my graph right?
Even if these
Yeah, what's the one graph?
Did you understand it? And then
That's what I'm gonna do because